In Chapter 7, we're going to talk about energy and how energy is involved in the creation and breaking down of different types of compounds. And we're going to start with a few vocab words here, looking at some of the information about energy. We're going to talk about a little bit about potential versus kinetic energy and what those mean and what those are. We're going to discuss a little bit about energy, heat, temperature, what those relationships are with each other and how heat and energy can be exchanged from different things. Another important set of vocab words, exothermic and endothermic chemical reactions. And we're going to think about these, and we're going to go into some of this idea of these various different energetics between the different compounds. So first of all, let's start talking about the difference between potential and kinetic energy. The potential energy is energy stored in a system or energy put into a system. If we have a bowling ball, for example, and we put the bowling ball on top of a hill, we put energy into getting that ball up there. At some point throughout the history of its time frame, it'll probably roll down that hill. Once it has that motion and that movement, it's going down the hill, then it has the kinetic energy. So it's the difference between energy stored and ready to be used and then the energy that is actually moving that system or that compound. Obviously, there's a bit of a difference between when we're talking about something from maybe your physics class where we're looking at macromolecular things that are very large that you can see and we can measure the movement. So the speed and the mass of that would be part of that energy, the kinetic energy. But we actually, in chemistry, we measure these things based on pressure changes. So changes in work and then changes in heat, typically more so than the velocity something is moving at or the weight, because in chemistry sometimes those things are hard to see how fast molecules are moving or to know how much each individual atom is going to weigh at any given time. More examples of potential energy might be energy in a covalent bond. So if we have rocket fuel, for example, in these big rocket tanks here, we are going to be able to burn those to produce energy and produce pressure and thrust for that. So we can have potential energy, and then that can be converted into kinetic energy later on. So again, this exists in those natural attractions and repulsions of our chemical bonds that are formed. And we can think of these things as gravity or positive and negative charges, kind of can be the analogies here. Springs, we can put potential energy into a spring. Chemical energy, these are the energies possessed by those bonds between the different atoms or molecules that can be broken and reformed in maybe a lower energy state. So these things are stored in bonds. So it requires, to get some energy out, it requires breaking bonds. So a little bit of energy needs to be put in before we can ever get any energy out. So whenever we break any bonds, there's some energy required. When we form new bonds, energy is always released. But a lot of times these things are happening simultaneously or in conjunction with each other. So we have to look more closely at what exactly is happening to know if there's an overall change, increase or decrease in energy when a chemical reaction occurs. And that's what we refer to as the thermodynamics of a system. It's the change in energy, really. For kinetic energy, it's easier to kind of think about kinetic energy in terms of real things that you might be able to see. For a ball, for example, with kinetic energy, it might have different types of movement. So typically kinetic energy in terms of a physics course, for example, it would be 1/2 the mass of that thing that you're looking at times the velocity, so how fast it's moving, squared. So this is 1/2 mv squared. Similar to E equals mc squared. That's the similar idea. The c instead would be the speed of light, and that's talking about light. So you've heard of Einstein's theory. It kind of is based off of this idea of kinetic energy. for different compounds. So we're going to be looking at vibrational energy. So molecules can vibrate, and the more energy they have, potentially the more that they will vibrate. We're going to have rotational energy. Molecules can have rotational energy where they'll be able to spin. Sometimes, not if they're solids, they don't have rotational energy anymore, but they would have vibrational, but not rotational. Solids also wouldn't have translational energy, so they're not able to move with each other. They're stuck in one location. But all three of these things can be related to the kinetic energy of a system. One way that we can look at this difference between potential and kinetic energy is with this little roller coaster diagram. It's kind of fun to watch. We can see as we go up the roller coaster, we increase the potential energy, and as we go down, we increase the speed at which the train is going. So we're going to actually increase the cars, we're going to increase the kinetic energy. So here we're at the top of the roller coaster. We have the highest amount of potential energy. As we go down and we get down all the way to the bottom, we have the highest velocity, 20 meters per second, with the highest kinetic energy. And then we'll start to kind of lose some of that kinetic energy as we go back into potential energy, where we have more. We're not as high as we were originally, so that's a little bit less, and we're still moving a little bit. And then we can kind of continue to go through that roller coaster to transfer different things through the system between potential and kinetic energy. And this is kind of a similar analogy to what's going to happen with different compounds as they go through kinetic energy. As they go through chemical reactions, they'll have different amounts of potential and kinetic energy associated with them. We can't really know much about the potential energy until we have defined the amount of the maximum amount of kinetic energy in the system. So in order to know what that potential is up here, we basically have to know what the velocity is at the bottom. So this is kind of an interesting part about chemistry, is that we can't really know how much potential is in a molecule and in the bonds of that molecule until we break those apart and then see what kind of energy is released or required for that reaction to happen. So this is just a quick example of, we're not going to go through the math of this or worry about this chemical equation right now. I just want you to kind of see that this is a way that we can determine the kinetic energy, the potential energy of the system. If the kinetic energy here is given down here as 2, we plug and chug basically. The mass is 500 kilograms, the velocity is 20 meters per second, half of that, so that would be equal to the about 100 kilojoules, or 100,000 joules, right? That's 100 kilojoules. That would be the amount of potential energy. That's the amount of kinetic energy it has here, and therefore we can relate that to the amount of potential energy at the beginning, right? When we were up at the top, this was all full of potential energy. At the bottom, it's all kinetic energy. Energy is one of those things that are maintained within the universe. We can't create or eliminate energy. It has to be transferred somewhere. So either you have it as kinetic energy or you have it as potential energy. It doesn't go away, so it has to be conserved. That's the conservation of energy law. So if we have 100 kilojoules of energy down here, that means that the potential energy was equal to that amount of energy. Another interesting concept is kinetic energy can be transferred. So if we have the movement of these carts here, and they can bump into the next one, we can transfer that energy from here to the car in front of it. And so that, just like we can kind of think about roller coasters and cars and bumper cars or whatever you want to think about, those molecules in chemical reactions can transfer their energy. And we're going to talk about that in just a moment when we talk about temperature and heat transfer. So really what we want to talk about now is this idea of kind of moving from roller coasters to actual molecules and their movement. And remember, we talked about vibrational, rotational, translational types of movement, and they all of these on average will have different amounts of it. So each different element within a tube or within your flask of liquid, they're all going to have different amounts of energy associated with them, different amounts of kinetic energy. So some will have more, some will have a little less, But the average, there's going to be an average of those things. And that's really what we talk about in terms of the temperature of a system, is typically looking at the average of all of that energy in there. It's not, the temperature doesn't tell you the high and the low, it tells you kind of the overall amount, the average kinetic energy. So you can see on the top, the average is probably lower in this compound than it is for the compound on the bottom. So that the greater the movement, the higher the temperature. And we're going to talk about those values here. Here's some terms here. The higher average kinetic energy gives us a higher temperature. They're faster moving molecules. Now, temperature versus heat. Heat is something that's transferred. So when we talk about heat, we're talking about we're going to transfer this energy up here, just kind of like how we bumped the little cars in the roller coaster. Those bumped into and increased the velocity of those cars and increased kind of the temperature. So heat is always, this form is always transferred between objects. So which sentence here is correct in regards to heat transfer? Pause and take a second to think about these. And when you do, hopefully you'll recognize, if we look at heat is independent of kinetic energy of a system. So it's not independent. Heat is transfer of kinetic energy. So A is incorrect. Heat cannot be transferred. Heat is transferred, so that is, or heat is a transfer, so that's not necessarily correct either. As kinetic energy from A is transferred to B, so as this heat or this energy is transferred to B, box A gets cooler and B gets warmer. A slows down and B speeds up. Yes, that one's correct. And then as kinetic energy from A transferred to B, this is the opposite essentially as C, so this one's incorrect. So C was the correct answer. So based on what you know about heat transfer, what do you think the best way to keep heat transferring from box A to box B would be? So think about that, and this should be one of, we'll talk about this in our discussion boards. Please post your answers to that. For the heat transfer, we're going to also talk about this in another way as well in just a moment. So in that question, I asked about putting something really thick and solid or something that was really low density. And what's actually interesting is the low density thing actually keeps from energy transfer from one thing to another, because there's nothing there to transfer the energy to. So if you have good thermoses, if you have like a Yeti, for example, those are kind of all the rage these days. What actually they do there is they pull a vacuum in between the outside and your liquid or whatever you're putting inside, or your ice. And what that vacuum does is it lowers the density of what's in here. When we pull a vacuum, we take the molecules out. And then when we have energy come in, or heat, we have molecules out here bouncing against here, and there's nothing to transfer that to because this is devoid of molecules. And so then we don't conduct energy through as heat into our liquid or whatever we have inside. So with really good insulation, we generally have a vacuum. Now sometimes they'll have a reflective lining as well to keep any radiation or any electromagnetic or from sun or any ultraviolet or other electromagnetic radiation. That'll help reflect that and keep it even more cool inside as well. So it's kind of interesting. We might also think about, well, why then do we put insulation in our house? Isn't air less dense than, the insulation we're putting in? Well, that's a little different. Generally, you want that insulation inside for your house, for example, if you're insulating. You want it to be really low density, but you want it to keep from the currents from mixing in your attic or in your walls. Those actually create drafts. They'll move and allow for that convection, allows for heat transfer from one molecule to another, and then that also reduces the amount of how much energy is reduced. So the insulation keeps that from happening, and actually you don't want to have this be a really thick and dense insulation. Funny enough, I was at Home Depot buying some spray-in insulation for something just to keep critters out of my basement, and it was funny because some of the bottles said about how they were more dense than other bottles of compound or the insulation foam. And I was kind of laughing. It's like, well, you don't want it to be dense. You want it to be pretty thin if it's good insulator. Now, maybe you want more density to keep, things from chewing through it or something, for example. But it's kind of interesting. The less dense it is, the better it is at preventing heat transfer. That's also typically why we use metal pots and pans for transferring that heat really well from the stove, whatever, if you have a burner or an induction or whatever it is, into your food. It transfers that heat very effectively. Over time, things will come to equilibrium, which is what means that they basically kind of regulate themselves and they come to the same position where we're not going to have as many things that are going to be maybe getting hotter. There are others that are oppositely getting colder. And so you can see here, if we start with something really hot and something really cold, you put them together so they can have that heat transfer. They're both going to eventually become the same. So this is kind of the idea of equilibrium, where we're going to bring these back down to the more common levels here. Thermometers also run using this kind of idea, where if it's really cold out, those things will come to equilibrium and the energy is transferred maybe from the thermometer out into the cold until they all have the same average kinetic temperature. And what happens is the amount of fluid within that thermometer is going to be calibrated. So when it gets really small, because the kinetic energy is small, then we're going to be able to say, oh, this is, freezing point for water. And then when we put it into boiling water, the kinetic energy of that system changes. These things move around more. And so that increases the pressure, and the volume actually will change inside that thermometer. And then it'll have a larger volume. And then this again is calibrated to temperature. So at a certain temperature, it'll say, oh, it's larger in size, so now it's 100 degrees, maybe it's boiling for water, for example. So that's kind of how thermometers work and how temperature is measured. Now I'd like to relate energy with chemical bonds and how those work with each other. So typically there are always going to be some attractive forces. So we have these protons in the middle that are positively charged, and we have electrons in the outside. And it's kind of the same as the gravity and the ball analogy. The closer these positives and negatives can get to each other, the happier those compounds are and the lower the energy state is. And most things want to get to the lowest energy state possible. So the closer that negative charges can get to positive charges, that's a lower energy state for that system. And those are the things that we're going to be looking at here. So atoms generally are attracted to each other. When we spoke in earlier chapters, we know that there are some different types of orbitals that have space for electrons to fit in them. And so when we bring these things together, these electrons can share orbital spaces. So they can happily be in the same spot, even though they're both negatively charged elements or subatomic particles. The positives are far enough away so that they're happy, but we then increase the amount of area that the electrons can be in, and we also provide them more opportunities to interact with positively charged elements. When we get these closer, energy is released for the formation of bonds, but when we break them apart, it always requires us to put some energy in to break those bonds apart. Let's look at just a specific example of this in a chemical reaction. So if we're looking at methane gas plus 2 units of oxygen gas, we'll react to form carbon dioxide gas plus water, 2 units of water in gas, and then that is going to actually release heat. When we're doing this, we have to break some of these bonds and reform new and different bonds. These bonds are stronger and the electrons are closer to the protons in these resulting products. And that gives us, because there is the potential goes down, we have higher potential energy here. Now this creates heat, and we have a lower potential energy in these molecules. That heat is released. So we still need a little bit of energy to break and reform these new bonds, but overall the system, the energy is released in the system. So let's look at this. When we're looking at the chemical bonds, we have the methane here, we have carbon and 4 hydrogen, and then we have the oxygen gas, and these are together. So these bonds need to be broken, these oxygen bonds need to be broken so we can reform these new molecules on the right. The methane and the oxygen, these are actually weaker bonds that can be broken more easily. And then the formation, this releases more energy than it costs us to break these apart. So this is a vocabulary word, the exothermic. So an exothermic reaction is where products have less chemical energy than the reactants. So these have less potential energy, and this chemical reaction that happened releases heat. So heat leaves the system, and this heat is kind of treated as a product. The reaction temperature gets warmer, the temperature of the system increases in this example. So this is exothermic. Exo kind of meaning out, and endo is going in. Endothermic reaction, kinetic energy can be converted to chemical energy. So a lot of times we're putting energy in to be stored as chemical energy. It absorbs heat from the surrounding, and the Q is heat in the system is positive, so we put energy in. And we kind of treat energy in this instance as a reactant. So we have to put energy in for it to happen, and the temperature of the system typically decreases because it's absorbing that energy. Another example is this, maybe it's not the temperature, but it's actually absorbing sunlight, for example. So carbon dioxide and water absorbing sunlight. This is the process of photosynthesis. We're going to activate and create larger compounds of sugar and then create oxygen. So these have more potential energy than these reactants, and we have to put that solar energy in for these to be created. All right, which of these do you think is an endothermic process? We have the sodium ion and electron fusing to form sodium, burning wood, methane, and that's breaking down into carbon and hydrogen elements, a bomb exploding, or water condensing. Which of these do you think would be an endothermic reaction? And post that in the Blackboard space for answers for the lectures. So different kinds of equations in chemistry will be called thermochemical equations, and that's actually when we have some of the information about energy involved or heat involved. Usually we're going to be talking about this under standard conditions. So if it's at room temperature, for example, not negative 25, but just 25 degrees Celsius would be around room temperature, an atmosphere of pressure, so normal pressures at sea level, and then 1 mole of compound. So if we're doing standard conditions, we can have chemical reactions just so everyone knows about what's going to happen when they do this chemical reaction, whether you're in Australia or the United States or Russia or wherever you happen to be, you will be able to predict and know how much energy is needed or going to be released from a chemical reaction. So this is kind of an interesting idea, and it's something that is why chemistry can be so useful for understanding what is going to happen and what to make predictions for what things might happen here. An example of this is just we're going to look at nitrogen plus hydrogen gas. So these two gases coming together and forming 2 moles of ammonia. And so this is a really important, this is the Haber process. Fritz Haber was a German chemist who actually developed this process and allowed it to be able to happen. This is actually releasing some energy, and this is a lot harder than you would think based off of the fact that this releases energy. There's a lot of nitrogen in the air, and ammonia was a long time before the world wars. This is what was really limiting the population, is getting nitrogen out of the air and into a usable form that can be used as fertilizer. So this is a really important process that happened in the kind of around the Second World War and allowed our population to explode, really, is this process. But this, under standard conditions, we're talking about 1 mole of this, 3 moles of that, generating 2 moles of the ammonia. And this is going to be exothermic because it's releasing energy. So this is kind of where I wanted to stop. This isn't, we're going to kind of get into most of the time now. We're going to generally, instead of the amount of, this is in joules, sorry, this got pushed over here. This is kilojoules of 92.38 kilojoules. Kilojoules is a form of energy. We're going to also talk about this as calories, and your book also talks about calories a little bit more as well. So we'll kind of go back and forth between the two, but typically when you're talking about food and food things, we're talking about calories instead of kilojoules. But the same idea, really, it's all chemicals breaking down, and it's amount of energy that's associated with it. So we'll talk about the next section. We'll more talk about thinking about this in terms of biomolecules.